Hello and welcome back to Computational BME. In this lecture we'll be discussing open methods for root finding. As you'll recall from the last lecture, in root finding we're trying to find the root to typically nonlinear systems of equations. And basically we're trying to take an equation f of x that equals 0 and find the values of x where that's true. Last time we discussed bracketing methods, which is the bisection method. And as you remember, you take a look at this function here, that a root as shown. The bracketing method required us to specify a lower and an upper bound on this root. And then on each iteration, we're going to check whether the true root is in the lower interval or the upper interval and adjust our limits accordingly. So on the second iteration, for example, we would adjust the lower bound, and on the third iteration, we'd adjust the upper bound. Basically, the bisection method is a slow but steady or convergent method that hones in on the actual result. In this lecture, we'll be discussing open methods that take a somewhat different and sometimes faster approach. And so if you think of an initial guess for x0, shown here, the basic idea is we're going to trace back to our function here and look at the tangent line, or the derivative at that point, and we're going to look at where that crosses the 0 line. We're going to set this as our next x1, and on the next iteration, we'll repeat this calculation again, and as you see in just 2 iterations, we got awful close to the true root. And so in these cases, the open methods can be much faster. However, you'll notice perhaps that these open methods can potentially diverge, that they're fairly sensitive to the initial guess of the root. For example, if we had guessed a value back here, then our tangent line may have hit an x value over here, which would trace up the next tangent would be very far from the true root. And so we'll be looking at the scenarios where these open methods do work and also where they don't work. So the Newton-Raphson method is actually the most popular method for root finding, and it uses open approach where, say we've got a initial guess xi, we're going to trace up to where it hits our function. We're going to compute a tangent line right here, and so that's now our xi plus 1. And when we compute that tangent line, we needed to know the slope, or f prime at xi. And so the basic approach here is that we're again looking at this initial guess, computing the tangent line, and looking at where that crosses our 0. And so one way to derive the equations for this is to look back at our original Taylor series. If you remember, when we did a first order approximation, we had this equation, and then we want to find where xi plus 1 makes f of x plus 1 0. And when we rearrange these equations, we get the following result, that the next guess for our root is given by the last guess minus the f of xi over f prime, or the derivative of xi. One of the things that's really nice about this Newton-Raphson method, as we had indicated before, is that it can converge quite rapidly, and based on the Taylor series, we can have estimates of the error, and that can be given by this equation, where this is saying that the true error at the I plus 1 step is given by this ratio of derivatives times the true error at the last step squared. So basically, at each iteration, the new error is going to be the square of the last error. And so that means that our algorithm is quadratically convergent. So let's now look at how to apply this Newton-Raphson method to a simple example. We're going to be finding the root of this function f of x e to the minus x using an initial estimate on that root at 1. So there's our x0 right there. And so we're first going to need to calculate the derivative of f, and we also need to know the true root so that we can compute our errors on these. Okay, so now let's plug these into our Newton-Raphson equation, and we get this. And so then when we look at the first iteration, we get this result that our guess of the root at that point is 0.5371 with just a relative percent error of just a little over 5%, which is really not too bad for our first iteration. And when we do this for the second iteration, we get a result of 0.5670, or a relative true error of just 0.03%. So we can see that this method is converging quite rapidly. So to give you an idea of what this looks like on the plot on the left, we had our first value x0. We trace this down here and take a tangent line roughly here. This was our x1, and then we take another tangent line down here. So we rapidly converge down to the root reasonably quickly. So we'll point out a couple of the main areas that can cause this method to diverge. The first is that if there's an inflection point near the root. So if you have a function that looks something like this, and say our x0 is here, then x1 kind of overshoots the root on the left-hand side, and if you trace this back on the very next iteration, we get back to an x2 that is reasonably close to x0. So in this case, the result is oscillating around our root and not converging on the answer that we want. Another case that can cause problems is if you've got portions of your function that have derivatives approximately equal to 0. As you can see here, if we started out something this, and the tangent would give us an x1 here, might have an x2 here, but then at x2 the derivative is now close to 0, and so the derivative is going to give us a root estimate that's very far from our root. So you can see how this could really diverge once you get at portions where the derivative is close to 0. So there are a few different tips that you can use to avoid these problems. The first is that these open methods, such as Newton-Raphson, really depend on a good guess for the root. The second is that you need to have some sort of built-in checks for whether your solution is diverging, and so one way to do that is to have a maximum limit on the number of allowed iterations. Third, when you do find an answer, you want to go back and check that your root actually is a root, but by making sure that f of xr is really close to 0. And for cases where the derivative is 0 right near that root, these methods are going to break down because it'll kind of force the problem to diverge as you're getting closer and closer to the root. And so there are modified methods that you'll need to look into if you're encountering that scenario. Again, you can check most of these issues by plotting your function before you go and start a root finding exercise. So one of the limitations to the Newton-Raphson method is that we needed to specify the derivative f prime of x. And so there's another method called the secant method that is related to this where we don't need to do that. So it looks like this. So if we have a function such as this, and instead of taking just one value, if we had two estimates for the root, then we could use the backward divided difference formula to compute that derivative. So as you'll remember from when we talked about differentiation, that this was our equation for the backward divided difference, and if you plug in that approximation into the Newton-Raphson equation that we had before, you get the following result. And so as you see, we no longer need to specify the f prime of x function. However, this does mean that we do require two guesses. Another method that is frequently used is called Brent's method, and the basic idea is that it combines the best of the open methods, such as the secant or the Newton-Raphson method that we just discussed, with the bracketing methods, such as bisection, that were often slower but didn't have the convergence issues. And the basic idea is that the Brent's method goes back and forth between these two approaches using the open method when possible, but then if the solution isn't converging, it switches back to the bracketing methods to ensure convergence. So to summarize some of the main points we discussed in this lecture, open methods can be converging really quickly in a quadratic way if they're working, but there are a number of cases when they diverge from the true solution, and so we need to watch out for that. The Newton-Raphson method is using the derivative of our function and one estimate for our root, and it uses that to compute tangent lines to find the root of our function. But if we don't have that derivative function available, like it's difficult to take that derivative, then we can use the secant method, which estimates that derivative using the backward divided difference approximation. And so in this case, we require two estimates for our root. And in many cases in numerical methods, there are advantages and disadvantages of any particular method, and the Brent's method is a nice example of a hybrid method that combines the open and bracketing methods for what might be the best of both worlds. Thanks for watching.